Uh-oh. Looks like I still have my background up. But hi, everybody. How are you today? It's great to see some familiar faces in the chat. You might notice it's a little bit darker. There's a little more shadows where I am right now. It's because it's pretty late here now. Actually, the sun has set where I'm living. So, yeah, normally I do streams in the morning. So it's a little bit of an adjustment. Hi there, Tech Rex. Good to see you. Welcome to the stream. Really excited for what we have here to share with you all. Yeah, so first of all, how has everybody's Hack Week been going? I hope you've been enjoying your time. Does anybody have any session that really stood out to them as just a ton of fun, or any other feedback for us? We'd love to hear the feedback and to get a sense of how you felt about the sessions. I'll put it up here if anybody has feedback. Rolf says having a lot of fun. That's great. Me too, actually. I've been having a ton of fun. We had some great mini events and some great workshops. Speaking of, I wanted to actually follow up a little bit because we've been having, we had a great show turnout for our No Light event, and I wanted to highlight some folks and their accomplishments at No Light. So I'm going to first highlight a user who is Cookie. And so I will just send a message to them. We're judging them now on stream, because I was asked to let them know when we're going to judge them. But the assignment was to recreate the Major League Hacking website using a single HTML file. And this was the result. This is the original MLH website. And here's Cookie's version. I'd say that looks pretty good. Super impressive. Way to go to Cookie. Hats off on that. And then we also had a submission from Ralph. And I wanted to show Ralph. So this is excellent. Ralph says, actually, this seemed even better than October's Global Hack Week. I'm so glad to hear that. So thank you for attending and for that nice compliment. And just send me the repo. Well, let's take a look at what Ralph submitted. So this is great. Look at that. We have even some like dynamic stuff going on here. The background staying fixed. And a lot of really impressive stuff here. I wonder if this works. Can I actually follow ML Hacks on this? Oh, interesting. Get a Twitter post. Is that really what that links to? No. That must just be my the latest tweets from my feed or something. But that's very cool. Very impressive, Ralph. And so, yeah, this is great. Let's actually see. Can we read any of these articles? Maybe not. Oh my gosh. Look at that. That's great. Excellent work. Ralph, those are great. Well, so if you haven't already, I wanted to make an announcement to check in for today's event. This is super important because it lets us know what folks are interested in and what kinds of content you'd like us to bring you for Global Hack Week. So don't forget to check in. All right. So today I want to start with a review from what we did last time. And this is going to be a PowerPoint that I have set up here. So let's try and present that. It's kind of tough for me to present. Let's see. Present this PowerPoint slide share. Great. All right, everybody. So this is from yesterday. I just wanted to present this because I wanted to give you all a bit more context about our data. So yeah, let me see if I can actually connect to my second screen here. Sometimes that'll help me if I want to use a speaker note or anything like that. All right. Let's see. Presenter view. That's exactly what I wanted. I love how easy things have just gotten over time with technology. Okay. So everybody, welcome. This is our slides here. It's pretty simple, but I just wanted to cover this a little bit for you. So, you know, this section is called Introduction to Climate Data Analysis. This section of the workshop series, and I just want to talk about how important climate data is. It helps us track weather patterns, understand climate change, and it's really important for things like agriculture. Where should you plant the crops? Urban planning. Where's the best place to build houses versus conservation, and disasters, like if you have an earthquake. Or if you have an extreme flood, actually would be a better example. So all that stuff is super important for climate science. Climate science plays a huge role. And this ERA 5 data set that we've been working with is provided by the European Center for Medium Range Weather Forecasts. This is a center which has really good data on global climate. And so that's why it's used so widely. And it's great that we can just download it for free. Anybody who has access to our little Python notebook can do that. And so a lot of the stuff we're using today and in our workshop, in our previous workshop, is around Python and some packages that are specially designed for scientists and for geoscientists especially. So we did a little bit of visualizing wind patterns. And so we visualized wind as a vector, which means that it has a direction and a magnitude. So if you remember, we had our vector representation of the wind, which had U and V. U was winds that were going eastward or westward, and V was winds that were going northward and southward, where positive was east or north and negative was west or south. And so because we can analyze these components separately, it lets us, gain even more understanding of what is happening in the climate. I think I showed a few examples last time of how the wind could go north to south, and that could and converge at the equator and cause a lot of rain to happen there. And another thing that wind can tell is if there's a storm coming, their wind will typically increase. If there's a cyclone or something like that. And so now I'd like to talk a little bit about sea surface temperature. We didn't actually use sea surface temperature that much, but just know that it exists, and we aren't using it that much for our snow prediction, um, but it's a really useful thing to have in a lot of cases. We had maximum and minimum air temperatures. So this was some data that we got. It's super important to monitor air temperatures because it helps us understand weather patterns and extremes as well. If you have an extremely cold day or an extremely hot day, it will have an impact on agriculture and on humans and on wildlife. So you need to know about this sort of thing. It's very important. All right. So air temperature, by the way, has a very big impact on snow, which was one of the things that we were hoping to predict in our workshop series. And then finally, as I mentioned, we had our snow density. And we could talk a little bit about how snow density is important for climate and hydrological studies. And we will look a little bit today at snow in more detail, but this is an essential factor for the climate system. First of all, snow holds a lot of water. So in the wintertime, we get a lot of snow and it can store water so that in the summertime, the snow melts and the water can be delivered to communities, right? So this is actually a very big, important component of the water supply where I live in California, because we have big mountains where a lot of snow falls, and then that snow is stored for the summertime, the springtime, when it comes down and in the form of snow melt. And we can use that water for drinking or for growing food. And we did some precipitation analysis. We looked at the precipitation data to understand how it was accumulating. We saw a lot of activity in the tropics and not as much outside of that. So that was interesting to see. So that's sort of where we're at. And we're actually going to encourage further exploration today. That's kind of what we're going to get to today. Because we're going to see how technology, once again, can have a huge impact in this field. So we're going to end the slideshow. And hopefully you all could see that slideshow. Sometimes I get nervous that I'm not presenting my screen. So just send me a message to let me know if you could see that or not. But we're going to go ahead and now review our previous notebook to freshen up on what we did last time. All right, so I will definitely present that now. Let me put this in another window. Oh, now my stream is in another window. That's great. I love working with two monitors sometimes. Okay, so let me share this code notebook. By the way, this code notebook is available in Discord. So if you have the Discord, it's right there. But we're gonna go off of it today. So we had a bunch of libraries that we imported into our environment. Oh, I'm going to actually take off this check-in comment too so that you can really see a lot better. But does anybody remember some of these libraries? I'll just leave that as a rhetorical question because I want to just kind of explain them once again. These Bodo 3 and Bodo Core. Bodo is how we get S3 data from the AWS cloud, right? So we can access S3 data using using our Bodo 3 client, and we actually can give it a authentication so that we can access private data. But in the case of ERA 5, it's public data. So this is public data. So no need for a signed key. We don't need that. And then we also have these libraries, which some of them might be familiar. I'm sure a lot of you know about the matplotlib library, which is good for plotting things. But maybe less of you know about these other libraries. So we have this library xarray, which is very widely used for making maps of things, as is CartoPy. So that's another Python library. And, the main application of these libraries is to science. So it just goes to show you how much technology and science sort of go hand in hand. All right. So then in this next cell, you might remember we got the bucket. This public data source for ERA 5 is in the ERA 5 PDS bucket. And we connected our client, our Boto 3 client, to S3 using an unsigned configuration. So because it's public, that's totally okay. We don't need to sign it with any kind of authentication. Okay, so this was an example of how the data was stored on the ERA 5 servers. We had the year followed by the month, and the directory was data. And then we could put the data file here. Okay, and so this was how the data files were named. They're going to be named also according to the year and the month and the variable. Right? And we also had a metadata file which kept all the information about which variables were available through the server. So this function here, download data, was able to download this weather data as if it was given a month, year, and variable of interest. And so we actually built that out, right? We had this data key string and this data file string that we could pass into the download file method associated with this client object. And that allowed us to retrieve the data from the ERA 5 server on AWS. Once we retrieved that, we could open the data set because it's now been downloaded locally. So we could just totally open this up and there's no problem. Well, we went ahead and tried it out. So we did it for the main.nc file. We specified the path for March 2019, just to give an example of a kind of month and year combination that you could use. And then we opened up this file, which was main.nc, and we got this information. Okay, so it's telling us, first of all, a lot of coordinates. So these are the coordinates for the latitude, longitude, time. How's the data shaped? For example, in this longitude, it's telling us that it recorded a value every 0.25 degrees, right? You can see that. And then in time, for example, if you just click on this little coin stack, it tells us that it recorded a value at March 1st, 2019, and then another one at March 1st, 2019 at 1 a.m. Okay, so we're actually seeing that the times are incrementing by 1 hour at a time. So that tells us that the data is stored hourly. Okay. And then we also saw the data variables that were available. So one of the data variables that is available is the northward wind at 10 meters. And then another one is the eastward wind at 100 meters. Now, we didn't really get into that, but you can. I'm not going to list them all, but you can see that they're all here, and you could refer back to them anytime you want. To download a different variable at a different time. Okay. And then this was our code that we ran to download all of these things, these variables of interest. And so, we had wind speeds, temperatures, precip, and ocean. We didn't end up using ocean, but for our training. But the goal was actually to train a model to predict snow, right? If you all recall, on our last part, we were actually interested in downloading weather data for Norway, Oslo, Norway. I think Ralph gave us this suggestion to check out Norway. So yeah, really cool problem to have. Sometimes you don't always have a way to measure the snow, especially if it's really far in a remote area, right? It would be hard sometimes to maybe tell how much snow is there. You can't send somebody out to make a measurement. Of course, in Oslo, you definitely can. There's plenty of people living there, but just in general, it might be kind of tricky. So you can definitely see the application for a for a model like this. Okay. So we actually defined a new function which was called getTimeSeries, and it uses the .sel command. So I'm actually going to show you where that comes from because we didn't go through that yesterday, but today we'll go through it. So I'll actually share with you this method. So you can see we have the xArray method .sel, and it operates on a data array object. So you need to have a data array object. In this case, we've just given it an arbitrary argument, which we call DA. So any DA that gets passed into this function, we will do the select method on it. And we said that the return of this method would be a new data array, which is given by selecting the index labels along the specified dimensions. So that's what's here in this indexers argument. So we could pass anything in there, a time or a location. In this case, we're going to pass the location of Oslo, Norway. And there's also a method argument here, and I didn't get into this last time either, so I wanted to be kind of detailed about it now. And you can see that there's several methods for selecting a value if there's an inexact match between your coordinate that you pass into the method and the actual array itself. So for example, we put in this really specific location for Oslo, Norway, but you might remember from our metadata that the latitudes and longitudes happen every quarter degree or so, right? So for that purpose, we need to find some way to match up the coordinates of Oslo, Norway with the closest nearby location in the data array. And that's why we chose method equals nearest to really get that location. Okay. All right. So now I wanted to scroll down and show you how we used this in practice. So let me show one of these. All right, so here's how we used the getTimeSeries, this select method in practice. And we did a Fahrenheit actually, which is kind of funny. But yeah, so we said, why don't you select the time series for maximum temperature and minimum temperature? And we used a data array. So we put in the data set taskmax, and then we selected a particular variable, the only variable that's actually stored, by doing dot and then the variable name. So that gave us our data array. And then we got returned to us a time series. So you can see these time series up here. And it kind of makes sense because this is, by the way, if we do this, I think maybe it'll be even more clear. Oh, I need to define this, I guess. All right, I guess I need to run these. I guess they didn't stay overnight, even though I thought they would, but I guess not. But yeah, so we plotted these, and it kind of makes sense because if you remember that graph, it's increasing over time. So at the beginning of March, it's early spring. It's still kind of cold in Oslo, but then over the course of the month, things tend to warm up a little bit. So that's kind of related to what we see in the data. We also did the same thing for the wind vector. So the wind vector being the two components here, eastward and northward wind. And we found that the wind speeds, generally speaking, we get these big gusts of wind that come and they go south. When they have a southern wind like that, that can often mean that the wind is coming from the poles, from the Arctic, because it will blow these cold air down into Oslo, right? So that's what you're seeing there when you have these big negative anomalies. And then we had precipitation, which we got the time series there, and it gave us these spurts. So precipitation only happens in one direction, right? It never rains from the air to the sky. It only rains from the sky to the air. So by definition, so you get these big positive blips, and those are storms, right? Those are rainstorms. A lot of them were happening in early March, it seems. And you could even try to match up some of these things. I mean, look at this 400 around hour 400, which is maybe like 10 days into the month. You get a big increase in precipitation, and you also see a large negative wind that's bringing polar air down. So you can see how these variables are kind of related to each other. All right. So now we also talked about standardizing, I think, and why we would want to do that for a machine learning algorithm. And the reason for that is because we have optimization algorithms that that choose the best pathway forward for a given machine learning algorithm. And in order to stay compatible with those algorithms, our data needs to be transformed into a standard scale. So those algorithms are kind of built with this standard scale in mind. And so that's why we do this. So let's see if this ran, by the way. Did we get? Oh, good. Everything is loaded up. So we're good. When we standardize, we subtract the mean from the time series, and then we divide by the spread. And that gives us our standard value. All right. So then we essentially put that into a dictionary and store all of the data. And this is what it looks like when they're all plotted on the same scale. So you can see all of our data plotted together and how they interact with each other. So some of them correlate with each other. You can see that, like, for example, our temperatures, our minimum and maximum temperatures are very correlated. But then there's also points where they are not. So for example, this precipitation is very when it gets very positive, the northward wind speed gets very negative, right? So those are anti-correlated. And so there's a lot of information here. And the variables are doing different things. They're not always doing the same thing or behaving in the same way. So what we can do is we can potentially use these features to predict a target, which is the snow. Right, so I changed the snow variable from last time. Last time our snow variable was snow density, but I actually think it'll be easier to predict the thickness of the snow. So this is the and LWE stands for liquid water equivalent thickness of the snow. So we're saying how much snow, just in total mass, how much snow is on the ground. Is there a lot of snow? Is there a little bit of snow? Snow density is a little more complicated. It's saying how dense is the snow that exists on the ground. But in this case, we'll just do the thickness of surface snow. I want to actually plot this before we go further because we never got to look at this variable. So let's check it out. So you might remember that to plot, we need to use the plot command. So we'll do a mean across time to kind of take the time average. I'm not really interested in one location. I just want to, or one time period. I just want to know kind of generally where is the snow and where is it not. And then we'll just plot it. So hopefully this works out okay. Okay, yeah, it does. You can see we have a lot of snow in the polar latitudes. Maybe we could actually crank this down a little bit and just say, hey, if the snow thickness is 1, we'll just make that the yellow. Yeah, so you can see we have a lot more snow. And actually, our snow is only in the northern hemisphere, unless you think about the Antarctic, for example. But it's really confined almost completely to the northern hemisphere. The reason for that is because it's winter in March in the northern hemisphere. In the southern hemisphere, it's not. It's actually summer. So that's why we don't see that much snow in the southern hemisphere in our data set. But we're interested in predicting the snow in the winter. So maybe we can even tone this down a little bit more and we'll see even better the snow. Yeah, so you can really see now where's the snow, where's not. And what I'm doing is I'm just changing this threshold, this Vmax threshold. That's telling me where I should stop the color bar. So you see, I'm stopping it at a lower and lower value, so you can get all of these colors visible when the snow hits these numbers. If you had it cranked up all the way to 10 or even to 5, you just won't be able to see those smaller values. They look really faded out. Yeah. So, all right, let's go ahead and look at the snow in a standardized way. I'll actually make a little plot again, just like we did before. I'll plot the target. So our target is the snow. And you can see the snow actually peaks. We have a peak snow sort of in mid-March. And I think that's because this is the time period where we've had so many storms. If you remember our precipitation, we had a bunch of storms early in the month and they just build snow. But then once we get to the end of the month, things start to heat up and the temperatures start to go higher. And I think that's why we see this decrease in snow towards the end of the month. All right, so we want to build a machine learning model that's going to handle that. And the way we do it is we can build a feature list, a target list, and an algorithm. So for our features, we will choose the 5 variables, the 5 climate variables that we investigated at the beginning of this workshop. And we use this .t. This .t is to transpose the matrix so that instead of having these long time series and having five lists that represent 5 long time series, we're going to actually have a single long list, and then each of the entries in that list will be a set of 5 features. So that's kind of how the machine learning model likes to read. It likes to read a list of features instead of a time series. There are other machine learning models that do like to read time series. But in this case, we don't have that. We're just choosing a really simple approach. We're going to start with linear regression, which is really good for certain applications, but we'll try and see whether it's good enough for our snow. But yeah, so then in our target, the shape of this is we want it to be the same length as the feature array, but it will only have one channel, one value associated with each list of features. So that's why the target size will be the same as the feature size. All right, so we have about 700 points, which is enough for certain applications. You'll see that this will be enough data to get some good results. But okay, so let's take a quick break here. We'll take just a 10-minute break. And then when we come back, we will tackle the machine learning aspect of this project. So before we go, though, I want you all to think about a little bit, how is it possible to predict snow using these environmental variables? What sorts of information can we get from these features, temperature, wind, precipitation, that would make it plausible to guess how much snow there is, right? So we'll take just a 10-minute break, and then we'll reconvene and we'll discuss the machine learning aspects. See you soon. right, everybody. Welcome back. Lewis says, is this still live? Yes, we were just taking a brief break, get people some rest, get a snack, do whatever you have to do to be ready for the second half of the stream. So hopefully you all enjoyed that little rest. But before the break, we were trying to predict this snow density using machine learning. We're going to use some concepts from technology. The first model we're going to try is actually the linear regression model. So this is the model that you might have heard about in your math classes or your statistics classes, and it's the y equals mx plus b model, right? So you would take two variables and see how they relate to each other by plotting them x-axis and y-axis. And then you use an algorithm to optimize. And the way that you're optimizing is you're going to ask the algorithm to draw a line through this data such that the distance between the line and the points on the map are minimized. So that's why they call it a line of best fit, because this is the best fitting line to the data. Okay, so in order to do this, we are going to actually have sklearn model selection module, and we will use the train test split method from there. This is a method that allows you to split your data randomly into features and also into targets. So into train data sets and test data sets, your features and targets into train data sets and test data sets. So you'll use the training data to calibrate the model and its values. So in this case, we would use the training data to find an estimate of M and of B. But then we would use the testing data as an out-of-sample check on our model. So what that means is, the question then becomes, is our model good for cases that it has never seen before, right? So that's how we determine that, is we take things that are out of sample and we test on it. Okay, so we're going to assume that the features and targets are already defined as NumPy arrays. So we will have their shapes as such. The shape of the features data set is 744 by 5, right? Because we have 744 hourly data points and 5 environmental variables: precipitation, minimum maximum temperature, and eastward and northward winds. On the other hand, our target data was the snow water equivalent. So that was how much snow we had for each hour, right? And it's going to be an accumulation thing too, by the way. So the snow will have something to do with the accumulation over time. That's very important. All right, and so we split the data into training and testing data sets. And the way we do that is by typing xtrain, xtest, ytrain, ytest. And we place our features and target as arguments into the train test split method. And we have 2 additional arguments, which I will show now. The first is test size. So that's telling you how much of the data we want to use for testing versus feature training, versus model training, excuse me. And then the other argument is for the random state. So I'm setting the random state. This is where the randomization, kind of where they start, what seed they start on. And so if I set it to 42, it will always split the train and test data the exact same way. So I'll always get the same final number at the end. But of course, you could decline to have this random state, and then if you run the model multiple times, it will give you a different answer depending on what you do. I'm just going to put this back because I want to have that. Okay, so now the next step is to create this linear regression model so we can use the sklearn linear regression method to instantiate a new linear regression model. And then we fit that model using our training data. So we use the fit method and we pass our training features and our training target into the model to calibrate its parameters. So we're going to calibrate its slope and its intercept. Okay. And then we'll predict on the test set. So we use this predict method to identify what targets, what snow densities we would predict using our model and given the features that we define. So we've given a temperature, a wind, and a precipitation, and from those we're told to predict. All right, so we can evaluate the skill of the model by using a mean squared error, and we can evaluate a linear regression by just simply plotting its predictions next to the targets. And so we'll get that. But first, let's just run the cell. And we see that the mean squared error was 1.01. That means that on average, there was about a one standard deviation error in our model. And that's actually not very good, unfortunately. You can see that our linear regression model for the snow kind of floats around 0. So it basically predicts a constant average snowpack throughout the entire season. And that's not really very good, considering what we want to actually do. In fact, let's do a scatter plot and see what we get here. If we plot the target, which is the actual variable, and the predicted values. So we're plotting now on the x-axis. This is our, I'll just even specify it a lot, our prediction. And then our y label, I'll say real values. So you can see that just our predictions are pretty terrible against the real values. I'd say probably the only cases where we get a good one are when it's about average. And then maybe when we get a really extreme value like -1. But honestly, it's pretty much a terrible model. There's no skill at all. That's what we say. We say the model skill. So the higher the skill, the better our model is at predicting. Okay, so we're going to endeavor to come up with a different model, which is going to have improved skill. And I actually want to show you all a diagram, which is hopefully going to give you some insight onto what we're actually aiming for in this non-linear model that we're going to look for. Non-linear meaning it's not the linear regression model or anything similar. It can handle sort of more complex relationships. But let me just show you an image from Google Images. Hopefully this will help you understand a little bit where we're going. So this is a random forest algorithm, all right? What you're seeing on the screen. And a random forest algorithm involves an ensemble, and I like to think of it as a forest. Of course, that's why they call it random forest. But it's an ensemble of decision trees. So each of these trees you can think of like how you might decide something if you're playing a game of some sorts. So, for example, let's say that this first branch here, it could be on this decision tree 2, we're just looking at decision tree 2 now, it could be whether the temperature is greater than 5 degrees Celsius, right? Because I think if the temperature is greater than 5 degrees Celsius, probably we won't get any snow, right? So maybe then you choose down to here. And then the next question is, all right, well, it was colder than 5 degrees Celsius, but did it rain recently or not, right? Because if there was precipitation recently, probably there is snow on the ground. But on the other hand, if there's no precipitation, we might not have snow. So that could be an example of a tree. And all of these trees will think a little bit differently in the sense that they will choose different values on which to select one or the other, and then come at a conclusion by voting. So the majority wins in this case. Whichever decision trees, whatever they believe as a whole, is what the final result of the model is. All right, so I'm going to show you the random forest regression algorithm from sklearn. This is actually one of 2 random forest models that are offered by the sklearn library. And this one is regressor. So it means that it's for estimating the particular value of an outcome of a target. Classifier, we did some classification in part 1 of this workshop series, but now we're doing some regression. Classifier was just telling you which category the data belonged to. Now we're actually interested in predicting its value. So we learned about this a little bit last time, but in part 1, excuse me, but the NEstimators tells you how many of these decision trees you should build for the random forest regressor model. And so the more trees you have, up to a point, of course, but generally speaking, the more trees you will have improved model skill. The only caveat to this is the number of trees. If you increase it without just as much as you possibly can, like let's say 1 million, 2 million trees, there is a law of diminishing returns. So you won't get that much better of a model if you use 1 million, 2 million, 3 million trees than you would using 100. So that's why the default is set to about 100, and you can move it up or down from there depending on your data. And so there's all these other things you can play with, and we'll actually play with one of them today. But I just wanted to give you this documentation so that you can see what goes into the random forest algorithm to make it so easy to customize and to make it powerful as well. All right, so let's go ahead and go back to our code. And I'm actually going to just zoom into this so that you can see really well. But so I want to basically write the same import statement from last time. In fact, all this stuff we don't need to write again. But we're going to use the random forest regressor method instead of the linear regression method. And so the features and target are the same. The train test split is the same. But here I create the random forest regressor. And so I just straight up copied all of the arguments from the sklearn documentation and pasted them into this cell. But I changed 2 things. So I changed the number of estimators, and I changed the maximum features to be equal to 5. I found that these are really good improvements on the original model that allowed the model to have an even better accuracy at training and then predicting ultimately the snow. So that's why I chose to do that. And then in these next lines, I fit the model. So I fit the regression model on the training data. And then I did a test. So I predicted based on the X test feature list, I predicted the snow values and stored it in a list y predicted. So then we evaluated the model and we got the mean squared error by combining y-test and y-predicted. And then we sort of plotted these together. So I'll show you what it looks like. It looks a lot better than last time. So this is our mean squared error now. We've dropped the error by 0.44. So we used to have a whole standard deviation of error, and now we have less than half of that. So we've basically more than doubled the accuracy of our model just by choosing a different algorithm. We didn't have to add more data or subtract any data. We just chose a different model. And you can see that now the model can actually capture these big upslopes and downslopes of the time series. And so then I have this method I wanted to show you all how to calibrate the model. So if you want to calibrate the model yourself to figure out, hey, which of these, which value should I put in here for max features, for example, I built this function so that you can test it yourself. So if you had max features, you can just set that equal to a variable, A, let's say, and then fit the model. And so if you get the mean squared error back, that could be a measure of the skill of the model. And so if we run it for each of these values, 1 through 9, we can test whether increasing the maximum features that are allowed on a given tree will improve the model. And you can see that we get at 1, we get this value. It actually drops down here for 2. And then I suppose it goes back up. So, it can just be good to check these and see what's the ideal. I guess actually maybe 2 would be even better choice. I tried a few other models here. This one is the support vector machine, I believe, SVR, and got a mean squared error of 0.67. And I tried a gradient boosting regressor and got a mean squared error of 0.8. So you can see all of these methods, which are not as simple as linear regression, maybe not as interpretable as linear regression, but they did give a better accuracy. So we're involving more statistics in this than just linear regression. So I wanted to point out one last thing, which is that if we run this random forest method, we can further improve our data. So I want to actually show a scatter plot of these two. Let's show it. All right, this is pretty good. I mean, if we then were to do a linear, like just to see what the correlation is, we can use this linear regression method. It'll tell us the correlation. So we can actually just copy this into this, and then we'll just print out the R value. So this is an R squared. Let's do R squared of 0.88. That's really good, right? But I think we can do even better. And the way I'll show you that is by doing a rolling average. So we have our normal values, right? But we can actually do a rolling average on the predictions. So I'm just going to call this predictions so that we can actually have it here. And then I'll say rolling predictions, which will be our rolling average. So we'll do a rolling average of about 10. And then we will plot that as another color. Let's just plot it at the end. so that it's a different color than what we've plotted before. All right, so we get this green looking thing. And I think this is a lot better because it tends to smooth out some of these really poor predictions that are dragging down our data set. So let's actually plot this next, and we're going to do the exact same scatter plot, but we're going to plot the rolling predictions instead of the predictions, and we'll see how this score changes. Oh, it's actually not quite right because we need to pick, we can't use those last few values. I think rolling predictions actually starts at NaN values. So we actually want to get rid of the first 10 values because, of course, they don't have any rolling average to compare to, right? So we have to kind of get rid of those. All right, and if we copy this down into our linear regression method here, where we get the R squared, we see that our R squared was improved quite substantially. So we saw about a 5% increase in the R squared, meaning that an additional 5% of the variability got explained by our model just by doing a rolling average. And that brings us to the last point I wanted to make about this, which is that the random forest regression algorithm cannot really handle time series very well. So that's why it has all of these wacky predictions. You can see down here, it's saying that, oh, well, we had huge snowpack, and then the next day we had really below normal snowpack, and then the day later we went all the way back up to huge record-breaking snowpack. And the reason it's making those wacky predictions is because it doesn't know about the day before and what was happening on the day before. If it knew that, then it would have an even better skill. So maybe we should actually try doing this again with our snow from the previous day included as a feature. So that could be a future goal. But another way to see how adding in time, information about time, would be useful is just by doing this rolling average, because that's going to really help integrate some of the time information into each of these data points. So I hope this has been a really good session for you to learn about some machine learning techniques, learn about climate science, a really important topic. So we're going to finish up the stream for the day, but and have a little bit of a shorter stream today on account of the last of the workshop series. But it was really great to work with all of you, and I'm going to actually post this notebook on the Discord so that all of you can take a look and try to run it for yourselves. It's a really interesting problem, and I think that if you have any interest in climate science, there's a lot of demand for this type of work. So my hope would be that if you thought this was an interesting workshop, you would try to explore the intersections of science and technology a little more on your own. So that's all I have for you today. But thank you so much for joining, and I hope you enjoy the rest of your time in Global Hack Week. Take care, everybody.